So what is a thread? Up until now, every program that you have written has executed in a single thread. And what that means is your code is executed sequentially from the first line to the last line. Perhaps you have a loop that's causing it to go around, or you might be using recursion, which may alter the exact flow a little bit. But overall, it begins at the top and it runs its way down. And what that means is that there's a single path of execution. So from the moment that the program starts to the moment that it ends, the code is being executed sequentially in a single line without interruption. Okay, that's not really true. In reality, there are things that can interrupt your program that are outside of your control. When you are running on an operating system such as Windows or Mac or on Linux, there are other processes that are also probably running, and your operating system gets to decide which particular process gets priority on the CPU at the moment. And until 10 years ago, every computer only had a single CPU and a single core. So one piece of code is getting executed, and what the CPU scheduler does, which is a part of the operating system, is it decides which particular program is going to get the CPU next. There are natural things that take a moment in your code where your code can't really make any progress while it's waiting for something. If we think back to last week, we were dealing with file I/O and sockets, and those are two great examples of things that can interrupt the flow of a program. When you ask for a file to be opened on the file system so that you can read some data out of there, assuming that your file system is on a spinning disk, which it probably is on your laptop, there's actually a delay while the disk has to go and seek to the appropriate place and actually pull that data back. Even if your disk is an SSD, which is significantly faster than a spinning disk, it's still much, much slower than the actual memory that you have in your machine. So your program execution will have to wait while the hard drive or the hard drives are retrieving that information. Likewise, when we opened a socket and we tried to read and write information to a remote server, that remote server may not be as fast as your server, and so you may have to wait there. There are many other things that can happen that are called interrupts, where one program can signal that it urgently needs the CPU temporarily, and as a result, your program can get put on hold. So all of these details are just giving you the idea that when your program is running, there are other things that are deciding exactly which part of your program is running and how much of it gets to run at any given moment in time. And so that is the reason why we might want to be able to split our program up and allow multiple bits of it to run simultaneously. So let's take an example of some big processing job. For example, I'm going to read in a spreadsheet with 1,000,000 lines, and I need to do some math on that spreadsheet. Well, if I have to do that sequentially, and I only have a single thread, as it were, then that thread is going to start at cell number 1, and it's going to do its whatever math it needs to do, and then move on to cell 2 and cell 3 and cell 4 until it gets through all 1,000,000. But there's nothing about that particular job, assuming that I'm only adding like 2 columns together, let's say, as an example. So there's nothing about that job that says that I couldn't do 2 different processes that are running through half of it each, in which case I would accomplish the job in half the time. Or maybe I could do 10 jobs that are running simultaneously, each of them doing 1/10, and therefore I can accomplish it in 1/10 of the time. So that's the idea of breaking work up into smaller chunks and then letting each of those chunks run by themselves. And what we would call those chunks is a thread. If you have a machine that has a single processor with a single core, then in actuality, only one thread will be able to work, but perhaps at any given moment. But perhaps there are reasons why that thread might naturally get bottlenecked, where another thread can then jump in and make progress while we're waiting for the first thread to get unbottlenecked. And again, perhaps it's waiting for information to come off the disk or to write information out that will take a moment. While that's waiting, we can use the CPU to chug through some more of the lines and just get through stuff a little bit more efficiently. But in the best case scenario, you have a processor that has more than a single core. And at that point, we can actually break it up, and each of those cores can be running independently a chunk of your code. So thread number 1 can run on core number 1, while thread number 2 is running on core number 2. Now, if you're not familiar with what a core really means, when you purchase your processor, which is one of the things that's inside of your machine, somewhere on your motherboard, there's an Intel or an AMD or an ARM processor. This is true in your phone, it's true in your laptop, it's true in any desktop that you use. The processor might be a multi-core processor, or it could be a single-core processor. Today, most of the time when you buy processors, they're probably dual core or quad core, which means they have 2 or 4 cores in them. It is possible to get machines that have up to 100 cores, and when you're dealing with GPUs, which are graphics processor units that are used in gaming, it is entirely possible to find 1,000-core video cards where you can have 1,000 separate threads all running simultaneously. So when you buy your processor, you get to choose how many cores you want the processor to have, and each of those cores can at minimum be running one thread at a time. I say at minimum because there's actually some magic that the operating system can do, which is called a pipeline, where it can take parts of a job and it can run them in parallel even on a single core. So the operating system and the CPU determine how many of these threads can be run simultaneously, but you as the programmer don't really have to worry about that. If you do nothing, as you have done up until this week, unless you've ever seen threads before, you have a single thread and the processor will do the best that it can do, but it will only run it as a single thread. What we're going to teach you today is how you can specify that I want this block of work to be in one thread and that block of work to be in another thread. And to be clear, that doesn't inherently mean it's going to run faster if you run your code that has all this threading built in on a single processor, single core machine. Then in actuality, it will probably run at about the same speed, unless there's things that are blocking that it can work around, as if you had not written it with any threads. But if you do run it on a machine that has more than one core, which again is very common nowadays, then you'll see a substantial improvement, 2, 4, 8 times improvement in the amount of time it takes to process a large set of data. And that probably doesn't seem very relevant to you right now because most of the programs that we've written so far have been very small jobs. But in the real world, when you get a job, you're probably never going to deal with such small things where you write a program that calculates a Fibonacci or calculates a power. You're more likely going to get a log file that is 50 gigs of data that needs to be parsed, and you need to pull some information out of that log file. Or you're going to have thousands of people connecting to your server, and they each need to be able to do something simultaneously, so each one of those would be allocated to one thread. And very specifically, that is how web servers work. So when you open up your web browser and you type in, some URL, reddit.com, and you hit enter, your machine makes many connections to get all of that data back. And each of those connections is running in its own thread, which allows the CPU to split it up and do it faster, even though some of them may get bottlenecked by the network or whatever else. Okay, so in summary, a thread is a way where you put a block of your code into a single thread, and then you can specify that you want that thread to run. And you may have another block of code in another thread and another block of code in another thread. And then you don't really get to say very much about exactly when they run or what order they run in. I mean, you can specifically ask them to start and you can ask them to synchronize. It's actually mostly going to be up to the operating system to decide how efficiently it can do that. So your job today is to learn how to break it up and how to set up the threads so that the operating system can then make its own decisions on how to run that out. So getting back to these slides, a thread is a program's path of execution. I think that's fairly self-explanatory. Most programs that you've written up until now were single-threaded. That means that they just had one thread. If you had a circumstance where you're asking the user to enter in some information on the keyboard and you're also doing some graphic rendering or a GUI like we did a couple of weeks ago, then bear in mind that if it's all in a single thread, the work that it's doing to draw the lines or draw the GUI is time that it cannot be processing anything else if it's all single-threaded. So ideally, anytime that you have work that can be broken up, you would specify that they can be run in their own threads. All right, so it's actually quite easy to do this. This is not very difficult. What's going to happen is you're going to define the function or the worker that you actually want to do stuff. You're going to create a thread and tell it to run that work that you just give, and then you're going to call start or run on the thread in order to get it going. Okay, so multi-threaded applications deliver potential power increase by running concurrently. Multi-threading means that multiple lines of a single program can be executing at the same time. The operating system gets to decide who's doing what. Threaded programs can be definitely used for anything that's time consuming. I will tell you that if you're in the graphics world or you're in a game design world, you're going to use threads a lot, because it turns out that graphic rendering is a very time consuming thing. Calculating, for example, that you have a light source up in this top corner and you want the light to be cast from there, and tracing where every ray of light is going from that light source, and then where you have shadows, that's a very intensive job. And so that would be run on one core, while you might be doing the bad guys or the good guys movements in another core, while you might be doing the background rendering in yet another core, or in many other cores, because you may have one for the trees and one for the rocks and one for the water and whatnot. If your grass is moving because of the wind, you'll probably have a core or multiple cores dedicated to just moving the grass around in the wind, because again, it's a lot of work to actually calculate how that would look. All right, so if you have multiple cores, multiple processors, this makes it, you have to be very careful if you have any kind of shared memory that is being used across the threads, because you have to be careful that you don't have race conditions where two different threads could update at the same moment. I'll give you a quick example of that. You have a bank account, which probably has very little money in it, thank you, pandemic, but you have a bank account and you have a debit card, and you might have two debit cards. So what would stop you from running to two different ATMs at exactly the same moment, putting your card in, typing in your PIN number in both of them? At the same moment, they would both think that you have the same balance. If you then withdraw $20 from each of them at exactly the same moment, there's a race condition, because you have to be careful in the coding that one of those doesn't just get lost at the time that you're doing the update on the balance. It's very, very important that you keep track of the fact that one is currently changing the balance and the other one needs to be told to wait until it has the ability to change the balance. So that's an example of a shared memory. The shared memory in that example would be your actual balance. And you had multiple threads, which were the people that were putting their cards in and taking out money. So anytime that you have anything that's shared across the threads, you have to be very, very careful with that. Okay, so this is approximately what things are going to look like. You have your main method up at the top, and you're going to call start on each of your threads whenever you're ready for them to get going. And what we're trying to show you down here is, if there's a single processor, then this program is just going to switch back and forth between the three threads. So it may be that thread A runs for, a fraction of a second, and then it'll get to a stopping point because it's waiting for something off of the disk. At that point, thread B will be picked up and it will run for a while until it reaches a stopping point. Thread C will run for a while, and so on. But if you're on a machine that has 3 cores, happy days, all 3 of these are going to start off at the same moment, and each of them is going to execute completely irrelevant of the other ones, and this program will get done in a third of the time. All right, so how do we actually go about do this? Well, you're going to either extend the thread class, which is what you can do in either Java or C#, or you're going to implement the runnable interface, which is something that you can do in Java. So if you're extending the thread class, it might look something like this. So we go off and we create a new object or a new class. In this case, we're calling it myThread, and you are always going to extend thread if you're going to do this. Inside of this object, you're going to have a method called run, and that method is going to have whatever work it is that you want that thread to do. So creating that class by itself, of course, doesn't do anything until you actually use it. So down in our main method, we are going to instantiate that object. So same as you've always done, it's going to be a myThread called th, which gets a new myThread, and that instantiates the object up here. And then you're simply going to call th, which was what we called it, .start. And that tells it, I now want that to run. And you may have more than one of them. And of course, I'm going to show you a bigger example in a few minutes here. All right, if you're going to do it with the runnable interface, which there are a couple of advantages to doing it with the runnable interface over just extending the thread, it works very similar. Runnable is actually an interface, so you're going to implement the interface. So myThread implements runnable. Again, it's going to have a run method. Again, it's going to have the code that you want in here. And again, you're going to instantiate it. And the only thing that's different here is that when you create it, you're going to create a new thread and pass it that object and then call start on it. So you can do it either way. The example I think I'm going to do in a moment has the runnable interface, so you're going to see that again. All right, so here is a sample of a full Java program, and this one is really doing nothing useful. It's just doing some counting and just to show you what would happen. So over here we have our main class, and it has its normal main method, which takes in the usual string arguments. And what it starts off doing is it's instantiating the other object, which is what's over here. So it's creating an instantiation of that called MT. It's calling MT start, and then it's going on and doing a loop that's printing out some random stuff. Okay, so the important thing to know before I go talk about everything that's on the right, the important thing to know here is that normally I would have said this executes sequentially. It starts off in the main program, it's going to do this, then it's going to do this, then it's going to do this. And that's true. But normally when I say that, it would have waited for each of these to finish before it goes on to the next thing. And that is not true here. So when this happens, great, that's a normal statement. It instantiates the object. But when this happens, it immediately moves on to the next step, even though this may have work that may take 2.5 hours. So the code continues here in the main thread, and then simultaneously this other thread is going to be running off to the side because it was called start on it as well. So this down here is going to be happening at the same time that this over here is happening, and it's up to the CPU to determine exactly when each part of that happens. The two threads are presented to the operating system, and the operating system decides what it wants to do with them and which one can run. In this case, neither of them are doing anything where they're needing to wait for anything. The only thing that could possibly slow them down is that they are both trying to print, and of course the operating system is going to have to decide who gets to print first, which is an interesting question. All right, so let's take a look at this object that we created over here, the new myThread. It extends thread, just like we said, and it has a run method, which has to be there in order for this to work. And all that's happening in here is just we have a couple of loops. It's a loop inside of a loop that's printing out some stars, and then eventually a new line. So again, to be clear, if you were to take this code and stick it into Replit or stick it into IntelliJ, what you would see is these outputs and these outputs would happen intermixed, and it would be completely random as to what order they happen in. So it's completely up to the operating system. If you run it multiple times, sometimes you'll see a lot of these, sometimes you'll see a lot of these. It just depends on what the operating system feels like doing. In theory, if you have a multiprocessor machine, they should run simultaneously. So loop 1 here and loop 1 there should happen at about the same moment because there's different processes that are running them. Okay. There is a problem with all of this, of what I just showed you, which is that the run method cannot take any parameters. And what I mean by that is when we defined this run method over here, you note that it takes no parameters. There's two open close parentheses there. That is by definition, you cannot put a parameter in there. And that's sometimes a problem because sometimes you need to pass information to the thread in order to make the thread do something or to be able to work on a variable or whatnot. So if that happens, what you're going to have to do is encapsulate the data that you're trying to send as another object, and then you can invoke that object inside of the thread so that you can get the information over there. So that's what this second example does. So we still have our main, and this is our main, and what we're doing here is we're creating a new object called fin transactions, and that is this object up here, this class. It just has two public variables in it. So all we're doing is we're encapsulating those public static string and public static doubles inside of a class, and then we're creating a new object of that class in our main program. And then we're actually able to pass that over to the other thread. So when we create our new thread, in this case, we're actually creating two new threads. They are both going to be of type they're both going to be of type trans thread, which is defined over here. The trans thread extends thread, and we're able to pass two parameters into their constructors, and then the run runs without any parameters down here. The constructors are then able to access the actual object that was passed in, which is of this other type, so it can see all of the variables that we wanted to get in there. So that's a way that you can pass a variable into a thread, which of course is something that you will need to be able to do because the chances are the thread needs to actually be able to process some data. All right, so this is just showing you what the thread lifecycle looks like. So you have newborn threads, which is a new thread when it's instantiated. It's going to eventually get called start, which is going to put it into a runnable state. While it's in the runnable state, there may be multiple threads in that state. They may alternate back and forth, or they may rotate around depending on what needs to happen. And again, depending on what's blocking on any of those threads, if they're waiting for the operating system or they're waiting for something else. So you'll see sometimes a thread will drop into blocked because it's waiting on something. And then eventually when that gets done, when it gets unblocked, it'll come back up into a runnable state. And again, if there's only one CPU or one core, the operating system will keep trying to evenly give work or evenly give the CPU to each of the threads as best as it can. Eventually, the threads are going to all exit one by one, and you can tell when a thread has died. So it's important to know that you can create one, you can put it into a runnable state, it may turn into a blocked state and then go back into runnable and back and forth between blocked and runnable, and then eventually it will die, at which point you will be able to see that the thread has exited. So a couple of methods that you might want to call. You have a get name, you have a start and a run. You might wonder what's the difference between a start and a run. The method will start a new thread of execution by calling the run method. The method is the entry point for the thread. Execution of the thread starts from this method. So in run, you can, the method is the entry point. Yeah, I don't know why that's written that way. So you call start, run is what you will have inside the method or inside the object that you're trying to run. Sleep becomes an important thing. So at any moment in a thread, you can tell it to go to sleep. When that thread goes to sleep, it inherently is blocked because it's waiting for the sleep to expire. And at that point, the other threads will run. So if you want to make sure that no thread is being starved, when you get to a good breakpoint, you can ask your thread to go to sleep for a millisecond or a fraction of a second and let the other one take over. And then there's also the ability where you can just specifically say, I yield to the other threads. You can check to see, is it still alive? Because again, it will eventually die, and so on and so forth. So that's what's going on here. Thread synchronization is a thing that you might need to deal with. So you may have a block of work. So let's take the example of, we have a spreadsheet and it has 2 columns, and each of those 2 columns and 1,000,000 rows. Each of those columns needs to be multiplied together, and then we're going to find some other data from that. Maybe we're going to add all of those together. Well, as I said, you could break that up into 10 separate threads, each of them dealing with 1/10 of the rows. So the first one would deal with, if there's 1,000,000 rows, what's a tenth of that? I guess it's 100,000. So the first one would deal with rows 1 through 99,999. The second one would deal with row number 100,000 through 199,999. But eventually, you need to wait for all of those threads to get done before you're able to add together all of those numbers. So that's a circumstance where you would need some form of thread synchronization. After each thread has calculated what it needed to calculate, you then may need to go between all of them and add those numbers together to give a final answer in this example. So there's a couple of different methods that are beyond the scope of what we're going to talk about here, but I'm going to give you just the high-level idea. So there's the idea of mutex or semaphores, which are basically ways, a semaphore in the real world is a set of flags. If you've ever been on a road where it drops down to one lane to go across a bridge, there might be a flag person on either side who has a flag. Those are actually called semaphores. The person on one side is telling you stop, and the person on the other side is waving the cars through. And then once the cars have gotten through, they reverse. So the first person who was letting cars through now says stop, and the other person starts letting cars through. That's a semaphore. In computer terms, it's usually done by just setting a variable, and then everybody checks the variable to make sure that it is actually allowing them to run at a given moment. So these are various different ways of synchronizing between different threads. And there is a synchronize routine in Java, which allows you to call synchronize between the threads. Again, this is a little bit beyond the scope of what we want you to learn here, but I just want you to be aware that that's a problem that you might have to look at. And if that is an issue, you might want to look at mutex or semaphores as 2 of the more common ways of dealing with the fact that the threads may need to sync up at a certain time. It's also quite common that you simply just keep polling and asking, are you done yet? Are you done yet? Are you done yet? Okay, the thread is done. Now I move on to whatever my next step is. All right. So that's pretty much saying the same things that I just said. And these last 2 examples are just showing you what it would look like in Microsoft Windows. You can open up the Process Explorer and you can go to threads and you can see the different threads that are running for something. So as normal, I'm going to go through a different example than what's in the slides, just so that you have another way of doing things. So what I'm going to do is I'm going to write a horse race. And each of the horses, it's going to be its own thread. the horses are going to pick a random number and they're going to sleep for some amount of time. So it's a very boring horse race. So each horse is going to be told run, which is an appropriate word, and then it's going to pick a random number and it's going to go to sleep. When it wakes back up again, it's going to move one block down the track, and then it's going to pick a random number and go to sleep again. And you have 3 threads who are all going to be doing this simultaneously. And so what you end up with is a horse race where every time you run it, you're going to get a different answer because they're running. So I'm just going to show you what it looks like over here on the right first. I'm going to drag this window over so it gets a bit bigger. Okay, so you can see the 3 horses. This is state-of-the-art graphics here, definitely worthy of 2020. So horse number 1 seems to be in the lead, and he is chugging along quite happily. Horse number 3 apparently is sleeping a lot. It's a very sleepy day for horse number 3, and it looks like horse number 1 is going to make it to the end. Every time you run this program, you're going to get a different answer. You can also see that the program is still running, and that was because threads 2 and 3 had not reached the end yet. The program actually only ends when all of the threads are done, which is an interesting thing to keep track of as well. So you got to be careful that your threads do actually end, not that any one of them is in an infinite loop, because any one of them in an infinite loop means the program doesn't exit. All right, so every time you run this, you're going to get a different output, and that's simply because each of the horses is picking a random number every time that they get called, and they will eventually reach the end one way or the other. So let's take a look at the code for all of this silliness. So what I have here is I'm going to use the runnable interface, and so I'm defining a horse which implements runnable. And in order for that to be true, I must override run. That's the one method that is required that you create. So eventually I have to have a run, and inside my run is what's actually happening in order for that horse to do its thing. All right, so I start off with horses, and I have a static ID so I can number all of my horses. So every time a horse is instantiated, or you make an object of my horse class, you're going to get a new horse number. So you could theoretically run this with 50 horses and they will all work the same way. So I start off with horse number 0 as being the first number, because when I actually instantiate the horse in my constructor here, I'm going to say the horse number for that horse is going to be plus horse ID, which is the original 0. So the first horse will be horse number 1, the second horse will be horse number 2, and the third horse will be horse number 3, and so on and so forth. They also get initialized with a location of 0, which is another public integer that I'm storing in my object. Location 0 just refers to the leftmost location, and I'm just printing out their location by printing a number of spaces. Again, this is not exactly state-of-the-art graphics here. All right, so when a horse is created, we give him a number, him or her, a number, and then we set their location to 0, and then the horses are ready to live a fruitful life of being raced down the track for no apparent reason. When run is called, what's going to happen is it's going to pick a new random number, and this just initializes the random generator. The actual way that you get a random number is you call nextInt in Java. It's actually next in C#, as you're going to see. And that both of those methods take in a number. I'm asking it to pick a number between 0 and 10. And then I'm taking whatever number it gave me and I'm multiplying it by 100. And the reason that I'm doing that is because the sleep method, 1000 represents 1 second, because it is dealing with a 1,000th of a second increment. So if you pass the number 1 to thread.sleep, which is the sleep method, it will sleep for 1/1000th of a second. If you pass it 10, it will sleep for 100th of a second. If you pass it 100, it will sleep for 1/10 of a second. And if you pass it 1,000, it will sleep for a full second. So in the worst case scenario, this will pick a number between it'll pick a number that is less than a second every time. Right? So it's picking a number between 1 and 10, and I'm multiplying it by 100. So it will generally be a number between 100 and 1,000. Great. So you will find that in Java, and this is different in C, every time that you try to do a sleep, you must wrap it in a try-catch exception block, because it can throw an error when you ask it to sleep. And you might say, how can it throw an error when trying to sleep? And I would say, have a cup of coffee and then try to go to sleep. And you will fully understand how you can have an error trying to go to sleep. No, in actuality, there are circumstances where you ask for a thread to go to sleep and the operating system says you can't do that right now, at which point you will get an error here. It's relatively rare, but you always have to check for it in Java. In C#, it'll let you call sleep without trying and catching the exceptions. All right, so really nothing terrible is happening here. I initialize a random number generator. I have a while loop that sets, while the location is less than 50, that bar at the end, that's the end of the horse race, that's position 50. So while it is less than 50, then it is going to pick a random number. It is going to sleep for that amount of time, and then it is simply going to do location plus plus, i.e. move one step closer to the end. If you ask it to print horse, what you are going to get is that line of text that you were looking at in my very beautiful graphical output. So to be clear, horse number 1 would have printed 49 spaces, and then it would have printed the number 1, and then the bar is in position number 50. And the way that that's done is the number gets printed after we start off by printing up to the location that it's currently at, number of spaces, and then I print out the actual horse number, and then I print out more spaces, and then I print out the actual bar at the end. And so this all determines, this is why it looks like the one is moving across the screen. It's just printing out a line of text with a bunch of spaces and either the number 1, 2, 3, 4, whatever the horse number is. Finally, the only other thing that's in my horse method is I have a Boolean that determines have I reached the end, and that is simply returning is the location greater than or equal to 50. All right, so that is my horse object. And by now you probably learned that you can pause the video and you can grab the URL up here if you want to go play with this horse. Feed it some apples. I don't know what you're going to do with my horse. But anyway, if you grab this Replit URL and you pull it up in your browser, you can come in here and you can say fork, and then you'll have your own copy of the horse race and you can play around with it if you want to experiment with threads. Do it with 10 horses, or if you want to start a gambling ring. It's the pandemic. What else are you going to do? All right, so over here we have our main method, and all that's happening here is that I am instantiating a horse, H1, which is horse number 1, H2, which is horse number 2, and H3 is horse number 3. So I'm creating 3 horses. And then I'm instantiating a thread for each one of those. So the horses are, again, of type runnable. That is important if I'm going to pass them into a new thread. The new thread takes a constructor which must be of type runnable. So thread number 1, thread number 2, and thread number 3 will each be told to start. That's what begins my race. So at this point, 3 different threads are running on 3 different processors, if that's available, and each one of them is deciding how long it wants to sleep, and then it is moving its horse along independently. So the only other thing I got to do is actually see the output as to what's happening with the race, and I do that with a loop. While horse 1 has not reached the end, and horse 2 has not reached the end, and horse 3 has not reached the end, then do this really weird thing, which I'll explain in a minute, and then print out the current state of horse 1, horse 2, and horse 3, and then sleep for a half a second, and then do it all again. Okay, the reason for this really weird thing, which this is only in Java, in C#, you very nicely can say console clear. In order to clear the console so that it looks like you're not just seeing the lines after each other, but I actually want them always at the top, I'm calling it clear. And in Replit, that is how you clear the console, because reasons. Don't worry about that. Don't focus on that. You will never be asked or tested on that. Those are escape characters for ASCII that tell it to erase the current screen and move the cursor back to the top left corner, and you have to call flush because they don't by themselves actually get flushed. So that is what clears the screen. This is what prints out the current state of affairs. And again, I'm just going to let it run so that you can see what we're talking about here. What's actually happening is each time through, it's clearing the screen and printing the current state of the 3 horses, then clearing the screen, printing the state, and it's doing that every 500th milliseconds, which is every half a second. Every 500th. It's every half a second, whatever the correct word for that is. All right, so that's why you're seeing the blinkiness, because it's actually clearing the screen and then redrawing it, clearing the screen and then redrawing it. Looks like horse number 1 is going to win again. Don't bet on horse number 1. Rarely wins, but today it's having a good day. I don't know what to tell you. Apparently it is very happy. All right, the only other thing that's down at the bottom is if horse 1 reached the end, then print out horse 1, 1, and 2, and then 3. Okay, so this code is hopefully very simple and very easy to understand. I wanted to give you something that demonstrated the actual 3 threads running independently and being able to track how they're doing. And that is all you would have to do there, is just create an object that specifies how it all works. How does all this look in C# for my C# friends? You have something that's going to look very similar, but I'm going to run through it. You do have to use system.threading if you're in C#. And then we have our definition for our horse. It has the same static variable, so static int horse ID, which is used to number all the horses. And then it has its actual horse number and the locations. I believe that that is identical code for the constructor. One thing that is different is that I cannot call it run in this case. So you have to name it something unique, and then you're going to actually use the name of this method when you instantiate the thread. And I'm going to show you that just a second. So you'll notice that in Java, in that horse, there was a method called run. I cannot have a method called run in C#. It's got to be called something else. So I called it start race. Other than that, it's picking it's initializing the random number generator, same thing as we did in the other one. In order to pick a random number, in this case, it's rand.next. It still takes in the 10, and it's still picking a number between 0 and 1,000. The thread.sleep looks the same, although the sleep is capitalized, and I'm passing in the number, and the location is ++ing, all within that same while loop. So again, that code is not different. The print horse, I think, is literally line for line, except I substituted the appropriate print statement. So these all say console.write instead of system.out.print. And then at the very end, it does a write line because I actually want the carriage return when I print out the line at the end. There's the reached end, which I think is identical as well. I don't think anything was different there. So the place where things are a little bit different is in my main method, in my main class and my main method. I instantiate the 3 horses the same as I did before, but this syntax is quite different. So when I create the new thread, I create a new thread start, and I pass it horse1.startRace. So horse1 is the object for horse. Start race is the name of the method inside that object that I want you to actually start executing on. And thread start is a method that takes a method from another object. So you will always have this syntax where you specify the actual name of the object and the method that you want to execute inside of new thread start. Other than that, you then get to call start on there, and I think the rest of this code is pretty much identical. And again, if you pause the video for a moment, that is the URL that you need to grab in order to see the C#. And just to prove the point that the horses run in C# just like they run in Java, I will do a run of the horses in C#. So this is the lecture on threads. That's the level of detail that we want you to understand. You need to know how to create a thread. You need to know how to start the thread, and it's useful to be able to call methods in the... Wow, horse number 3 is apparently dead. Somebody do a welfare check on horse number 3. Ooh, that program is still running. He reached the end. Excellent. All right, so I want you to be able to create an object, create make it a runnable thread, and then actually call start on a thread and have work done. Of course, this is a silly example. Usually you would be doing something where you're processing data or something very structural and important. I make horse races. I don't know what to tell you.